And I need to download last Thursday's lecture from the clouds so that I can upload it to YouTube. So um, that's coming and not yet done yet. That's kind of a tonight/tomorrow morning thing. Since my daughter's a senior and the co-op that she belongs to is doing a graduation this year, sometime around about the last week of May, first week of June, I have all the senior stuff going on for her. She's getting senior portraits done tomorrow, so I have to take her over to the lady who we know who is a professional photographer to get that done. So my life is busy. All right, who am I still missing? I think I'm still missing 2 people. Yeah, I think I'm still missing 2 people. All right, let me start by going through the solutions homework. I uploaded this yesterday afternoon so that you can check and see where you went wrong if you made mistakes. So the first couple on the page are all about starting with molarity, which we remember is moles per liter of solution, and converting it over to molality, which is moles per kilogram of solvent. Hence, why you need the density as part of your given data. So if we look at the first one there, we have 2.5 molar sodium chloride. You have a density of 1.08 grams per milliliter. And my suggestion for the best way to approach these problems was to assume that you have a liter of solution available because it makes the math a little less messy. That would mean that my liter of sodium chloride solution has a mass of 1,080 grams. I know that within that 1,080 grams, I have 2.5 moles of sodium chloride. Periodic table, molar mass of 58.44. So of that 1,080 grams, 146.1 is actually due to the salt. Subtract so that you can figure out what the leftover is that is your water. We're assuming all of these are aqueous solutions because it says that at the top. And so now the 2.50 has a different denominator than the original one, which would have been 1 liter when you did it as molarity. This time you are dividing by your 0.9339 kilograms. Make sure you're moving your decimal place there. And it gives you 2.68 molal. Keep in mind, one of my also comments when we did a few of the examples for this was that typically, no guarantees, but typically your molality is somewhat higher than your molarity because of the fact that you have a different type of denominator going on. Instead of liters, you have kilograms. Instead of solution, you have solvent alone on the bottom. So looking at the second one there, this one is an ethanol solution, 5.86 molar. Your density was 0.927. Again, make your assumption that you have 1 liter of solution. My ethanol, and you might have had to go look this up, but ethanol was one of the molecules we covered in the organic chapter. This is actually part of the reason why we do the organic chapter first, is a whole bunch of these molecules you see again. It has a molar mass of 46. So do your 5.86 times your 46 grams per mole. You have 270 grams of ethanol. Do your subtraction, 927 minus the 270 to give you how much water is present, 657. Move your decimal place so that it's 0.657 kilograms. Finish out your last division. And like the one above, it does end up with a larger numerical value than your molarity, so 8.92. All right, more variations on a theme. This one, you are given molarity, but you are looking for percent by mass. You need some of the same data. You need the density, but you're going to manipulate your data a little bit differently here. I know that it's a 9 molar solution. I know that it's phosphoric acid, H3PO4. Start with your 1 liter, in this case, gives you 1,400 grams. Your 9 moles of phosphoric acid times a molar mass of 97.97. Big chunk of the solution is actually the phosphoric acid, so 881.73. This one is part over whole times 100, and that will give you a percent by mass of 62.9. If you rounded it and called it 63, that was fine. Then we get into the concept of like dissolves like. We want to compare each one of these things and whether or not they are likely to be soluble in benzene. Benzene having only carbons and hydrogens, 6 of each, meaning that it would be very, very non-polar. So if you look at the first pair, we've got ethylamine, which is the NH2 attached to the ethyl group there on the left. So it would be somewhat polar. Propane, on the other hand, those 3 carbons with all their accompanying hydrogens, no real polarity at all there. So the propane, the second molecule, would definitely be more soluble. Again, 2 similar molecules in the second set there. We have methane, which has just a single carbon and accompanying hydrogens. The other molecule having a chlorine atom. Chlorine is more electronegative. That would make that molecule somewhat polar, makes the methane more soluble in benzene. How about going in the opposite direction? Looking for what is more soluble in water. So you want something that is more polar. More polar probably means fewer carbons and hydrogens. So when you look at the first pair, both of them are alcohols, but the first one only has a single carbon. The second molecule has 3 carbons. That second molecule, which is propanol, would be more non-polar, not completely non-polar, but more non-polar than the methanol on the left. So methanol is more soluble in water. And then we have a pair of hydrocarbon, again, propane, versus acetic acid. The acetic acid has 2 oxygens in it. That would definitely impart much better polarity to it, which means it's going to be significantly more soluble in water. Then we head in the direction of colligative properties. Number 5 is based upon Raoult's law. Raoult's law uses mole fractions as part of the calculation. I gave you 450 grams of sucrose and 624 of water. So I actually need to know how many moles of each one I do, so that I did dividing each one by its molar mass. Sucrose, and we've seen sucrose several times before. It's a really common soluble substance when we're talking about aqueous solutions. So your 450 grams of sucrose is being divided by 342. That gives you 1.31. We had roughly 50% more water present there, 624 grams, but water's little. Water has a molar mass of 18. So I have 34.6 moles of water. Remember that when you are doing your mole fraction, you are putting the one that you're looking for on the top and all of them added together on the bottom. And typically your solvent, which in this case happens to be the water, is a significantly larger mole fraction, far closer to the 1.0 value. So we've got 0.964 times your given value, vapor pressure of water, implying that the water is pure, 31.8. Multiply the two of them together, it drops, not a lot, but nothing that we see in Raoult's law is going to give you a magnificent decrease in your pressure. Usually the decreases are fairly slight. You probably max of about 5 millimeters of mercury is about the upper limit of what you're likely to see. Having more than that, while not impossible, would probably be unusual. All right, switching over to freezing point depression. This one is linked to a lab that is coming up relatively shortly. I believe it is the B group people who are doing this in 2 weeks, I believe it is. Double check your schedule on that though. I just put up some of the stuff on lab for that. I haven't quite finished. I put up some information. I haven't put up the handouts that you need to print off to use in lab. So we've got a sample here that has 2.35 grams. It's non-ionizing. That's kind of a somewhat important point because we want to not have to worry about positive ions and negative ions increasing our colligative properties. It's dissolved in 1 kilo of water. The freezing point goes down 0.125, so it drops, obviously. Freezing point depression. What's your molar mass? 2-step process. First, you need to put your change in temperature, because water freezes at 0, and it drops down 1/8 of a degree. Your negative 0.125. The negative is actually not super relevant because change in temperature for this kind of a calculation is an absolute value. 1.86. You could have either looked that up in your lab book. It's also in your textbook. Yeah, Google works too. And that will give you a molal of 0.067. Now you have all the pieces to put into the equation of grams of solute over molal times kilograms of solvent. And this mimics one of the examples that I gave you. This one's small. This one has a solute of 35-ish grams per mole. Chances are it's something small like sodium chloride or potassium chloride or something along that line, instead of a big organic molecule. Same equation, slightly different approach. This time I gave you the molals of your naphthalene and benzene. Okay, note the order in which these are written. Okay, naphthalene in benzene. Benzene is your solvent. Naphthalene is your unknown. You don't actually need to know what the naphthalene's values are. It just happens to be your solvent. If you're doing freezing point depression, boiling point elevation, same equation that we used above, in that our delta T is your molality times your K values. Again, this is one that, because it was homework, I did not give you values for as part of the question. You needed to look up the K values for benzene. For boiling, the KB is 2.53. For freezing, the KF is 5.5. So you are going to end up with a 6.25 degree change for boiling and a 12.6 degree change for freezing. Make sure you are going in the correct direction. Freezing point depression, boiling point elevation. This is why you need to, and actually my page jumped again there. This is why you need to have them go in the appropriate directions there. Your boiling point will go up to 86.4. Your freezing point is going to drop to negative 7.1. Boiling goes up, freezing goes down. Last main colligative property here. We've got osmotic pressure being looked for in atmospheres. You have a 1.36 molar solution with a 22 Celsius temperature. Pi equals MRT. Therefore, 1.36 molar, your 0.0821, which is your R value that we also used in traditional ideal gas laws, and 295 as your corrected to be in Kelvin temperature, gives you 32.9 atmospheres. If you rounded it and called it 33, that was fine. Some people did the extra credit. Obviously, you didn't have to. I actually created this problem a couple summers ago when I was making jelly, and as I'm standing there waiting for my boiling point elevation, which is actually a mixture of the stuff you add to your solution combined with the fact that there's pectin in there too. But I simplified the problem a little bit and gave you 4 cups of juice, 3 cups of sugar. I also gave you some basic information there to help you along. 4 cups, 8 fluid ounces per cup, gives you 32 ounces. We've got 29.57 mils per ounce. You have a little less than a liter, 946.24 mils. I gave you a mass for sucrose, which is not completely and utterly correct, but it's close. And this gives you 750 grams for the sugar. Remember, you're doing molality. Okay, that's what it asks you for. So it's moles of sugar per kilograms of liquid. Make sure you're doing it in kilograms, move your decimal place, and you get 2.31 molal, which is fairly realistic. Like I said, I ballparked it a little bit when I created it, but I didn't make it too far out there as far as how close to reality it probably is. Questions about solutions homework? All right, let me talk about your upcoming test. So the test will go live. I need to turn it on so it actually shows up on your module, but it won't become available until midnight on Thursday. So after, basically, we'll have lecture on Thursday, and then you'll have, if you stay up that late, I don't know what kind of schedules people work. it'll go live at midnight. Typically, since we're doing all of this virtually, typically people tend to take the tests on one of the weekend days, but it does give you Friday and it does give you Monday. So you basically have a 4-day window to take it. It will shut down at midnight on Monday. And sometimes takes me a couple of days to get them graded because some of it is auto-graded. Like the way the test is constructed is kind of a mixed bag of things. There are some conceptual true-false problems. Most of those are 1 point apiece. There's about a dozen of those. There are some short calculation, short answer, and organic molecule questions that are 2 points apiece. Remember, we did all those functional groups in the organic chapter. And since the bulk of you have me for lab, that particular problem is designed to resemble the pre-lab from the organic lab, in that I just drew out a bunch of molecules, and I hope that this is decently viewable when you actually log into Canvas to do it that day. I took a picture, okay, of a printout of the page, because drawing diagonal lines with Microsoft Word is a pain in the ass. So I drew the diagonals by hand, and then I took the picture, and then I uploaded it to Google, my Google account, so I could download it and yeah, all that sort of thing. So hopefully when you look at the picture, you can see all the molecules there and then just like list off what their functional groups are. All of them are just one functional group only. Unlike some of the homework, where a couple of the homework problems had multiple functional groups in a single molecule, these are just kind of one apiece. So true, false, multiple choice / kind of labeling. And then obviously in the intermolecular forces chapter and the solutions chapter, there are problems. So the problems are designed to be relatively similar to homework problems, and they vary in points. When you're doing the test, it should show you how many points they are worth as you're going through it. Those are the ones that are not auto-graded by Canvas, so I have to go back and grade those by hand. It usually takes me a day or two to crunch through all of the grading. So like you guys will be done by Monday at midnight. I may, if I have enough time, grade some of them during the daytime on Tuesday, but probably the bulk of them will not get graded until during the daytime on Wednesday, prior to me coming to lab that night. So just kind of keep that in mind. It might take about 2 days before you see grades posted for test scores. You will have a 4-hour time window. Once you log in to the lockdown browser, it's not the one that has the camera, it's just you can't surf on it, okay? Because I don't really have to watch you. Also, not everybody has the same, like I have a webcam that's actually not part of my computer, it's a separate, and I know that other people do too. So I just use the lockdown browser part and not there's actually a name for it. Something about the watching one, the one that watches you while you do it. But anyway, don't worry about that part. You have 4 hours, 240 minutes from the time you start till the time it shuts down, which should provide you about twice as long as you actually need. The way the test is designed, there's 45 questions. Like I said, multiple choice, true, false, some like one-word answer things, and then some math. Based upon homework and all the things that we've done, I would not really expect it to take you more than 2 hours, but I did give you 4 because every now and then people have sluggish internet connectivity. So in case that happens, that's why I wanted to give you a bit more time. Questions about the test? And I will remind you on Thursday that it's about to be activated. All right, let me get rid of my solutions homework and get back to kinetics. We got partway into the chapter here. All right. I think the last thing that we were talking about last week was looking at the data and then using the data to help you figure out what your exponent is on your reactants. For kinetics, we are ignoring products. They come back to haunt us a little bit when we get to equilibrium in the next chapter. But from a kinetics point of view, we're only actually worried about the reactants. So we looked through the data for this, and we did some comparisons of when you hold your NO concentration still. At this point, we held it still at 1 × 10⁻⁻⁶. If you double your O3, your rate doubles. So this helps us identify the fact that your coefficient for the ozone O3 molecule needs to be 1. And then you look at the second set of data where we are holding the O3 at a fixed value and we're changing the NO. And it did something similar. When you double your NO, you double your rate. So both my A and my B ended up being a value of 1. And we had a look at K values. So it shouldn't really matter which line you pick. I picked the one that had an NO concentration of 1 to the -6th. My O3 was 9 to the -6th. My corresponding rate, make sure you pick everything from the same line, was 1.98 × 10 to the -4th. Crunch all your data. You end up with a pretty enormous K, but the only thing that means is that this is a fast reaction. K values tend to be linked to speed, not always, but tend that direction. So big K value for this tends to give you the idea that this is a speedy reaction. And then we kind of ended on Thursday talking about, well, that means if it's first order in NO and it's first order in O3, you are allowed to then add them together to call the whole reaction second order. All right. What if your exponents are not equal to each other or not equal to 1? I decided to do one that gives you a decomposition reaction here. We have acetaldehyde. So the CH3CHO is a shorthanded way of indicating that your oxygen is actually double bonded to your carbon. I know that looks weird. That looks like they're out of order, but it's an acetaldehyde molecule. We get methane and carbon dioxide as products, but we don't really care about the products. So I need to find out what the exponent is that goes with my rate law. All rate laws kind of look the same. They go rate equals K, something. So in this case, the something is your reactant, and we don't know what the exponent is. Remember, your options are 0, 1, 2, 3. Those are your only options. So if I look at my data, if I look the first two lines, 1.75 times 10 to the negative third, if you double it, you get 3.5 times 10 to the negative third. But look at your rate. My rate didn't go from 2-ish to 4-ish. My rate went from 2-ish to 8-ish. I quadrupled my rate. This is your indication that my exponent is a 2. Okay, think about this from an exponent's point of view. 2 to the, and we talked about this a little bit last week, 2 to the 0 power is just 2. 2 to the first, or actually, no, I said that backwards. Blah, blah, blah. 2 to the 0 power is 1. 2 to the first power is 2, meaning everything doubled. 2 to the second power is 4. So when I doubled my solution concentration, my rate quadrupled. It went up by 4. So this allowed me to identify that it was a second order reaction for my rate law. And actually, I just suddenly realized I left out my K. It's supposed to be rate equals K times CH3CHO to the 2. Yeah, I neglected my K. The K doesn't actually go away. So it's things you need to think about. Okay, if you are talking about your reactants, anything raised to a 1 is called first order. Anything raised to a 2 is called second order. 3 is third order. There is also the possibility of 0. Okay, if your exponent is 0, like I said, 2 to the 0 is 1. Anything that is 0 order means no matter what you did to the concentration, the rate would not change. One of the labs that is happening right before spring break, which is hopefully going to be a video, which fingers crossed, I'm going to film the demo after lab on Wednesday of this week, after lab tomorrow. I'm going to film a little 5-minute video of it, and then I'm going to give you all the data for it. One of the items in that particular reaction is 0 order. Here's a different one for your example here. We have NO2 and CO make stuff. If somebody tells me that upon analysis of their experimental data, my NO2 was second order and my CO was 0 order, you can sort of temporarily write your rate law as rate equals K, NO2 to the second, CO to the 0. But then reminding you, to the 0 power means it's just a 1. So technically speaking, it usually isn't even written in your rate law. You just get rate equals K NO2 to the second power, and it looks like the CO has just vanished. And yeah, it has, but it has vanished for a particular reason. It's vanished because we are doing or dealing with something that happens to be 0 order, meaning that no matter what concentration of carbon monoxide I used, it wouldn't change my rate. It also means that my reaction is second order in an NO2, but it's also second order overall, because there is no other contributing factor to this. So some miscellaneous information to kind of help you keep track of units. If you are dealing with something that is strictly a first order reaction, by the time everything cancels out appropriately, you will end up with whatever time unit. It could be seconds, it could be hours, it could be years, but it's going to be to the -1, which basically means it's on the bottom. It's like a per second or per hour as your unit. Second order is molarity flipped upside down. So it's liters on the top and moles on the bottom. And time is also still on the bottom. You're not going to see a lot of third order. There's a little mention of it in your textbook you can look at. For the zero order ones, this one is molarity with time also still on the bottom. So information to kind of help you keep track of things a little bit when you're trying to find out what your K values are. If you want to make sure that you are ending up with the right math, you can also keep track of your units as a way to kind of double check yourself. I wish I had a way to cut apart this little visual here, but it was the only one I could find that I liked. So it actually kind of dumps all three of them there on the same line. But for instance, on that zero order reaction, if you were to graph concentration versus time, you get a straight line. Your slope is K. For the second order reaction, note all of these have time on the bottom, but your second order reaction, actually, I skipped the first order reaction, has natural log of concentration of whatever it is you're looking at up the side as your y-axis. For second order, you have an inverse. You have 1 over a concentration. And also note, your slope is positive on that one. Some of you have done the heat of vaporization lab already last week. Some of you will be doing it tomorrow. All or the graph that is constructed from the data should resemble the middle one there. Clausius-Clapeyron is a first order reaction simulation. We are only looking at change in, it's actually change in pressure as opposed to change in concentration, but it follows the same kind of dynamic as a first order rate reaction. All right, now let's look at them in a little more depth from a little more mathy point of view here. So if you write a first order reaction, so rate equals K, whatever your reactant is, remember the ones are implied, not written. You could also rearrange that to say rate is equal to change in concentration over change in time. What if you integrate it? And yes, there's, I think, a little blurb in your book that tells you about the why this works. Take it on faith, okay? Don't worry too much about the why it works. Calculus, integration. Calculus, which I'm not super great at. Trig, algebra, yeah, cool. Me and calculus are not great in the best of times. It takes a lot of kind of brain power for me to kind of dig through that. Like I said, take it on faith. Once you integrate this, though, this is a first order reaction. You get natural log of the original concentration at time 0, over the concentration at another time. Now, this is another problem where I had with Microsoft Word. That natural log doesn't just affect the top item there. The natural log actually is on the outside. If I had a MathCAD embedded in my computer, I could maybe convince it to draw big, tall parentheses that have the A0 and the A inside the very vertically elongated parentheses. Let me switch back over to my whiteboard for a moment just so I can kind of show you what I mean. All right, so we would have big parentheses like this, and you would have your A0 on the top here. And you would have your line, and you're going to have this on the bottom. And your natural log would actually be on the outside of this giant set of parentheses. Like I said, Microsoft Word is kind of problematic in terms of writing really large parentheses that encompass more than one line. So you can go back and have a look in your book to get a better view of that. So things we need to think about for this. Your concentration of whatever it is you're looking at, A, is dependent on time. And so since we're natural logging it, that means your y-axis is natural log of concentration. But if we think about this in terms of the very traditional way to get a straight line, y equals mx plus b, your y is the natural log of a, your slope is negative k value, and your y-intercept is the natural log of your original concentration. And so, and I sort of vaguely recreated the graph from above down here just to kind of rehash it a little bit. So here's your line that you're seeing there, and you can figure out what your slope is. Your slope is your k, because often knowing something about the k is kind of the goal, at least from a lab point of view, less so from a problem point of view. What do we want to do with this? All right, cyclobutane. Cyclobutane being a very odd looking square molecule. This is me switching back to my whiteboard. Clear my drawings. All right, cyclobutane. All right, C. Because it's got to have 4 carbons, and then each of my hydrogens needs, or each of my carbons needs to have 2 hydrogens in order for it to be a nice, stable molecule with all of the appropriate hydrogens for the designated numbers of carbons. I hate using my touchpad to do this. It's super annoying. Anyway, this is your cyclobutane molecule. It's really rigid. It's also not completely stable. Hence why when we look at it here, it says decomposition. Okay, if you heat it up a little bit, because 500 Celsius is fairly hot, you can get it to start falling apart. So I have a K value for this. My K value is 9.2 times 10 to the negative third. Note my time unit is in seconds. I wanted to figure out how long for 80% to decompose. Okay, let's take a moment and think about what that actually means. Not 80% left, 80% gone, 20% left. So my original concentration is the 0.1 molar. Take 20% of 0.1, you end up with a much smaller value. You end up with 0.02. I have a given K value, and I can put everything here into my equation. I can put the 0.1 over the 0.02. I'm going to do a little algebraic rearrange there so that I can bring my K value to the bottom on the other side. I natural logged after I divided. I divided 0.1 by 0.02 and then took the natural log of it. That gives me 1.609. My K is still there. Finish dividing by K. And I end up with a T value of 1.7 times 10 to the 2, or 170 seconds. Fairly fast reaction. 170 seconds is not quite 3 minutes for that particular amount of decomposition to take place. What if I knew the time and not the concentration? This is where the anti-logs come into play. And we saw this before when we were dealing with the Clausius-Clapeyron equations, in that sometimes when your unknown value is within your parentheses and your natural logs on the outside, you kind of go as far as you can. And again, I just realized I have a small glitch here. This was supposed to be a parenthesis, not another zero. So K is the same. This is the same equation. Okay, this is the same reaction. My K is still 9.2 times 10 to the negative third. But this time I know what the T is. Multiply those two together. At the moment, I'm kind of stuck because my X, my unknown concentration, is actually inside my parentheses. So I need to anti-log both sides. That gets rid of the parentheses and everything on the left-hand side, but it changes the value on the right-hand side. I now have 2.51. Finish your math. And so 100 seconds gave me 0.04 molar. Now think about the sort of logic of that for a moment. I'm going to scroll back up here just a little bit. All right. If it took 170 seconds to go from my 1 molar there all the way down to 0.02, well, if I don't let it run as long, I'm not going to go quite as low. So it makes quite reasonable sense here to then look at my value there and go, oh, yeah, I only let it run 100 seconds instead of 170 seconds. So the value of what's left is not quite as low as if I had let it sit there and do its thing for a lot longer. So 0.04 molar. Kind of think about the realities of this. All of these are based upon real reactions. They do kind of have to obey the laws of reality. Half-life. Half-life is used for many, many things and not just nuclear stuff. From a purely mathematical point of view, half-life, often abbreviated as T with a little sub 1/2, is how long for the half of your original, again, I'm finding all my typos in here, half of the original concentration of your limiting reactant to be used. This one has a fixed value. Look at your equation there. 0.693 over K gives you half-life. The 0.693 never changes as long as you are talking about first-order reactions. So since my daughter is taking science from me, since we're homeschoolers, one of the things that we did in terms of cell death was how long does it take for like all the cells to get killed off by the antibiotic? And we did it in terms of half-life, except we used M&Ms. So because you know how M&Ms have like the printing on one side and the back side is blank. So you shake up 100 M&Ms and you remove all the ones that have the M showing, and you get to eat them, of course. And then you keep on doing it until you run out of M&Ms. And this gives you a graph that displays half-life. So the same thing is actually true with reactants, in that half of your substance is gone for each aliquot, each chunk of time. Okay. This is also used extensively in medication. Okay, if you read the back of your Advil bottle and it says, you know, take 2 tablets every 6 hours. Okay, well, why wouldn't you take every hour? You know, might be the question you might think about, because wouldn't that be better? Well, the idea is that you want a certain amount of it to be processed out of your system before you take the next dose. And so because your liver and the enzymes that are present in it only process at a certain speed, generally speaking, you can calculate how often you should be able to take a medication based upon its half-life. Medications, for the most part, obey first-order kinetics. Now, there are a few that don't, but not many. If you look through pharmacology textbooks, there's only just a handful that don't quite work this way. So first order rate reaction depends upon K, doesn't depend upon how much you started with, which sounds weird, okay? So back to the M&Ms. If I have 100 M&Ms and half of them go away, I'm left with 50. 50 is half. Well, what if I started with 60 M&Ms and half of them go away? 30 is half, okay? But it's still half. It doesn't actually make a difference the quantity you start with. Again, this is specific to first order kinetics. All bets are off when we get to second order kinetics in a moment. So remember that hydrogen peroxide reaction that we were looking at way back at the beginning of the chapter. And one of the things we said was it took that really weird time unit, 2.16 times 10 to the 4th seconds, for it to go away by half. Well, if I know the T1/2, I can actually find my K. Put it back in your equation, T1/2 I know. 6.693 doesn't ever change. That's a fixed value. Do your algebra. That means my K value is 3.21 times 10 to the negative fifth. You can find your missing piece. Rules of algebra. If you have one equation, you can find one missing piece. All right. I'm probably not going to get through all of this, but we're going to do a little bit of second order stuff tonight. So second orders, definitely a little bit more complex. There's two options here. We're mostly going to tend toward the first one, but the second one is not really mathematically different. It depends upon if you had dramatically different starting concentrations. That would affect your data. So you could have A, whatever it is you're looking at, squared, or you could have two things to the first power. Your A to the first power, your B to the second power. Both are ways to get second order reactions. Like I said, we're kind of mostly paying attention to variations on the first one. Your equation is not quite the same because it doesn't have any natural logs in it. This one has inverses, 1 over something. So if you integrate to get the second one, you've got 1 over A, so that's concentration at some other time, minus 1 over original concentration, A0 for original, equals KT. Your half-life expression gets a tweak too. This time, it's not 0.693 on the top, it's just a 1. And this time, it does actually make a difference how much you started with. So your A0 is part of your half-life expression. So we're going to kind of tweak with this a little bit. We're going to say we have an ester and a strong base. We've seen esters back in the organic chapter. And we are going to, like I said, simplify this a little bit and presume that both my ester and my base are the same concentration. We know that this is a second order reaction with a K value of 4.5. I started with 0.020 molar. How much have I got left after 10 minutes? All right, start putting the pieces into the puzzle here. I don't know my A, my concentration at later time. I do know my A0. So I'm going to put the 0.02 on the bottom there. I know my K value, 4.5. I know my time. Make sure your time and your K have the same unit. In this case, I have minutes. So I can multiply the two of them together. That will give me liters over moles, and the minutes get canceled out. So 4.5 times 10 gives you 45. I'm going to move my 1 over A0 to the opposite side of the equal. So that means add it to that side because you're adding to both sides to get rid of it. Again, rules of algebra. So 45 plus 1 over 0.02. 1 over 0.02 is 50. And I just realized my spacing here looks really flaky. Let me push this down so it's a little more readable. Finish your math. My 1 over A is 95, so do your little algebraic flip. A is 1 over 95. I have a little more than half left. I have 0.0105. I started with 0.02. I didn't quite use up exactly half. And I did this in 10 minutes. Well, what is my half-life? How long does it take to use exactly half of it? So use my alternate version here. This is for my second order reaction. My T1 half is 1 over K times initial concentration. My actual half-life is 11.1. And that kind of makes sense. I used up close to, not quite exactly, half in 10 minutes. It would have taken a full 11 minutes and change to actually reach 50% gone. There is another class problem that we will pick up with on Thursday. You can read that in the next couple of days if you like. And then we have some other odds and ends that occur in this chapter also. But we're kind of about halfway through. Thursday, we'll get probably close to the end of the chapter, but not entirely to the end of the chapter because I don't want to make homework and tests occur on the same weekend. This probably means that your homework will end up being due on a week from Thursday. Basically, we'll have already finished the chapter and probably begun equilibrium before your kinetics homework is due. So tentatively, your kinetics homework will be due. And actually, I need to look at Google Calendar because I'm like going, my brain is going, what day is that? Today is the 16th. We have class on Thursday, which is the 18th. So your test goes live on the 18th. You have until midnight on the 22nd. So this will probably make homework for kinetics due on the 25th. So kind of pencil that in. Hopefully that also avoids a little bit the bizarre problem that I'm not sure how this is exactly going to affect us with SIS and part of the electronic system undergoing a systems update from the I think it said from the 26th through the 1st. So hopefully that means homework will have already been turned in, test will have already been done before we have to deal with the fact that the system might not be available for 2 days. Bad planning on the IT department part, in my opinion. Questions about kinetics? Or lab tomorrow? Otherwise, I will see about half of you tomorrow.